Continuing from the last video, in this session we're going to develop the simple demo further and show some of the advantages of using an RTOS in your embedded application development. This leads on to looking at our demo applications using an evaluation version of SAFERTOS. In the last video we looked at how to create a simple flashing LED task. In this video we'll show how using an RTOS enables easy code reuse and how passing different parameters into a task changes its behaviour. Starting with the LED example, what if we wanted to control more LEDs? We can reuse the task code and instantiate it multiple times. Be aware that each task still needs its own stack and task control block. All the tasks run independently, with the RTOS scheduler managing the timing. This shows the original Start LED code with a parameterized version for controlling multiple LEDs. The main differences are that each task requires its own TCB, stack buffer, and can take different values in the function arguments. Instead of creating one task, we iterate for the number of LEDs in the system, creating a task for each and assigning each one its own set of values as required. These per task fields can easily be set up as shown here. The stack will be the same space for each task, while the task parameters may vary. Here we see the parameters for 3 LED tasks, each driving a different LED with a different toggle rate. Now that we have a simple system with multiple tasks, it's natural to think about how they can communicate with each other. SAFERTOS supports the queue mechanism for tasks to communicate. Queues operate as FIFOs, with data copied in and out of the queue. Any queue can have multiple tasks sending to or receiving data from a queue. While multiple senders is quite common, multiple receivers would be unusual. Task interaction with queues can cause a task to block, either waiting to receive an item from a queue or for the queue to have enough space to place the data item on it. Queue events can also cause context switches. For example, if a high priority task has been waiting to receive data, when the data is placed on the queue by a lower priority task, a context switch occurs to wake the higher priority task. This shows how we create a queue in SAFERTOS. Because all memory allocation is static, the buffers used by the queue must be supplied by the application creating it. The buffer is simply a character array large enough to hold all items placed on the queue, and a small amount of overhead the OS needs for each queue created. Once created, the queue is referenced by its queue handle. An optional step is to register the queue. This is for debug purposes and allows the State Viewer debug tool to associate a name with a queue. As with all SAFERTOS API calls, the return code should be checked for errors. A common cause of errors is the queue buffer not meeting the system alignment requirements, or that the buffer isn't big enough. Having created a queue, this slide shows the API calls to send and receive data from it. As mentioned previously, data is copied onto and off the queue, which allows the variables to be reused as soon as the queue call has completed, without worrying about data loss. The blocking time is a count in RTOS ticks. If the queue is unable to send or receive data immediately, the task will block for up to this period of time. If at the end of the period the queue still hasn't received or sent the data, then the call will return with an error and the task will resume. Thanks for watching, and remember to follow us on Twitter for updates.